Else? Nobody? All right. Nice talking to you. Okay. All right. All right. I'm going to go to the notes here because that's what we're doing. And I got to go to these here. All right. So remember Friday, I didn't finish these. I'm actually going to show you something. Those that I had last year. Who did I have last year? One. Where do I have the last year people? Two. There's only two in this class? Three, four. Okay, I'll show you a document that I had last year on graphing quadratics. And then somebody asked, can you place what I showed them on the calendar? And I'll try to find it on last year's calendar and throw it on Friday because it really pertains to Friday and it'll tell me this next year. So, and actually, I'm going to go to it right now. So I threw at you, like real quick, here's how you graph quadratics. And I just threw a bunch of stuff at your face. Like, this is vertex form. So you get the vertex and then do 2 points above and below and graph it, and then you can answer questions on it. This is standard form. So you do the negative b over 2a. All right? Get that x coordinate and then go 2 above and 2 below. This is intercept form. Get the x-intercepts. The x coordinate of the vertex is right in between. Input, say it. You input that in, you get the y value, and then find 2 more points. Usually like you to get 5 points here. But how many people remember this document from last year? After we did all the forms, I threw this at my students. I actually shared it with the other teachers. It was up to them if they wanted to do it. And yours was blank. So, all right, put your attributes down. I don't want this to go. I'm better off just going up here. So you had to fill this in. When it's in standard form, it's the magic formula, negative b over 2a, f of that. But when you have vertex form, the vertex is h comma k. And you got to disseminate this form from this one. They have parentheses, but these are different. Those are the x-intercepts because if that's at x minus 3, for instance, if I threw 3 in there, this would create a whole 0 on this side. So I threw in 3, I got 0 as an output, 3 comma 0 is the x-intercept. That's different than this one. If this said x minus 3, I'd get 3 comma k, because this all would be 0 plus k. So some people really struggled with that. Those that didn't, just struggled with stuff in general, I guess. And then the axis of symmetry is these. This is just to show you the average of the x's comma over 2. That's where the vertex is. It's right in between. That's all that math means. Then I gave you these 3 different equations. I said, hey, find what you should on this one. Well, y-intercept is actually pretty quick. So I can find the y-intercept. This one, the vertex is pretty quick. So find that one. That one, those are the x-intercepts, so I could get those pretty quick. Then I asked them to foil that, and then in secret, Mr. Samuelis was a trickster. These are all the same equation, just in different formats. Anyone remember this from last year? No? Yes? Okay, had you work on it on your own and create your own. So the point was, you can have the same equation, but in 3 different formats that tell you 3 different things. All right. This one is good for a y-intercept, super fast. How to get the vertex? You'd have to do the negative b over 2a. Vertex form, fast. Hey, if I FOIL this out though, hey, if I FOIL that one out, hey. So I had to put all 3 of those together and graph the one graph. All right. So I thought that was pretty good last year. And I guess I could put that on the calendar. Gotta breathe more. All right, now it's time for piecewise functions. Can you say piecewise functions? Very good. I don't know if we did this last year. I have no clue. It's hard for me to remember if we did this in math too. It really isn't hard. What piecewise functions are is this is the domain. And the domain is different for different pieces of the graph. This is one function defined by 2 different pieces. The next example shows you a scenario like that. And actually, it's going to be the hardest example that we deal with at this point. So input, say it. So where do I plug in f of 3? What's your inkling? I give you a 50-50. It's either the top part of the piece or the bottom. Which one is it? Why would it be the top? Who said top? Why? Because 3 is, anyone? Greater than 1. So the point of a piecewise function is you have to plug this in certain parts of the piecewise function as dictated by the domain here on the right. So I have to plug that into the top, which is 3 squared 9. 3 times 2 is 6. That's 15. So it has to be in this top part, not the bottom, because that's not how the function is defined. Okay, that's easy. What's f of 0 then? Top or bottom? Bottom. 0 is less than 1, so that's negative 0 cubed, which is 0. What about f of negative 2? Top or bottom? Bottom. This is negative 2 cubed, which is negative 8 negative, which is positive 8. Now, I'm going to do this one. I'll just tell you what it is. Where's f of root 2? That's kind of mean. Is root 2 bigger than 1 or less than 1? Bigger. It's 1.4. I mean, come on. Root 1 is 1, so root 2's got to be bigger than that. So it would be the top one. I got a better question. What's f of 1? Which one do I plug that in, top or bottom? Legally, which one? It's got to be the top. Now, I'll show you what you do on a graph. There is a step off that you have to do when we actually graph. But that's 1 squared 1, 1 times 2 is 3. So it's 1 squared plus 2 times 1. So you don't plug it in the bottom, but when you make the graph, you kind of have to. And I'll show you what I mean by that. Okay, now go ahead and read this and see if you can fill this out. So go ahead within your group. I'll go ahead and go through these real fast. I made a major mistake last hour, though. I screwed up my scales. I didn't look at the scale, and then I really screwed up my equations of lines, which is eventually what we're going to do. Okay, so you do have to read, so there should be silence. Like as you're reading my questions. The only thing you shouldn't be able to do is the very last question, which is really, really, really hard. It's actually the hardest part of these notes. I think it's a little out of order. But I'm still going to do it like last hour. Really, really tough. Actually, if you get what I do at the end here, letter F, you're going to be in good shape for piecewise. Oh, just hit my, that just hurt my back. It's sore too, working out. Sore. Actually, doing a lot of swimming. Nobody cares. Where you, biking too, like the swim. Wait a minute. You want to tell you? Hot wires. By the way, this is one function, but it's in pieces. The function is just, what's his name? Easton's distance from home over time. That is f of x. That's what I want you to understand. It's one function, how far he is away from home at a certain point in time, but it's defined by 5 different unique pieces, 5 different, what we can create as equations. Okay, I think everyone's here. This is going in the trash. I don't collect and keep papers. Not doing it. Okay, so I hope you got a domain. 0 minutes to 75 minutes, right? Right? Okay, we can write that as an inequality. We are counting 0 as the start. At 0 minutes, you're 0 feet away, or miles. And then at 75 minutes, you're back to 0. And then there we go. Our range is 0 to 2.5. And then you would say you are at most 2.5 miles away from your home at any point during this traveling. It takes you 75 minutes to go from home to the 2 stores and back home, is what you maybe write for A and B. Okay, so f of 10, actually this was kind of tough. F of 10 is right here. What's really bad about this is 0.5, and then it goes by 4s. I screwed this up. All right, I didn't screw up this question, but I screwed up something later. I was quite embarrassed. But what is halfway between 0.5 and 1? What does that actually end up becoming? 0.75, and it's 0.7 at 10 minutes, you're 10 minutes, right? Yeah. At 10 minutes, you're 0.75 miles away. At 10 minutes. And then f of 50 right here, you're 2.5. So same thing. It's 2.5 and then blah, 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 blah. It's the same thing. At you're 2.5 miles away at 50 minutes. You're actually sitting in the grocery store doing your shopping. So I guess when you're moving around the store, you're not moving away from home. You don't count that. Even though aisle 4 may be farther away from home than aisle 3. Anyone? Or closer. Depends. Never mind. Who cares? What is the average rate of change? This is what I screwed up. What a fool. What is the average rate of change from 0 to 10? And this is what I did as a buffoon. I went like this and said, okay, here we go, folks. It's easy to find the slope. Rise 3, run 2. 3 halves. What's wrong with that? What is every mark here? It's a really awful number. Does anyone know what every mark here up is? What's every mark 2 up? 0.25. So then what is it only 1 up? 0.125. It's awful. And then every mark right is 1, 2, 3, 4. It's the same. We're 4 here. What a terrible marking. Terrible. All right, so that's 5. So this is 2.5 as well. So for every 1 mark, it's 0.125 up, and then right, it's 2.5. So when I picked this, I went 1, 2, 3. So that's 0.5. So fine, this is a rise of 0.75, right? But then this is a run of 1, 2, 3, 4. I guess it is a run of 10. So I guess I was making it a lot difficult than it should have been because it does end up on a nice thing here. So it's 0.75 over 10 minutes, right? So 3/4 of a mile. And then when I actually divide these, this is 0.075. And then what does that represent? And I did do this rise over run. So it's 0.075 miles. I hope I got the same thing as the other one. And then I reduce it down to a denominator of a minute per minute. Right? Okay, so that's how we would write it. If you left it like this, that's 0.75 miles per 10 minutes is how you'd label that one, right? Okay, so that's the average rate of change because you're along a line. Okay, in context of the story, during that part of the trip from home to the grocery store, I forgot where you went first. Oh, bank first so you can pay for the groceries. Makes sense. All right, yeah. What's the average rate of change from 40 to 44? I'm not looking up there. What's the answer? 0. That means you're at the store. You're not moving away from home during that time, right? Okay, so I'm not doing that. Piecewise, can you write an equation for the piecewise function that corresponds within this story? This is the hardest question. If you actually understand this, this is supposed to be my last example, but I'm going to go ahead and do it. We're going to do it right now and challenge ourselves. And it's really tough, some parts of it. So what is f of x? Your distance away from home over time. Unfortunately, there's 1, 2, 3, 4, and I ran out of highlighters. 5 different pieces for this. So there's 1, 2, 3, 4, 5 pieces to this function because there's 5 different things that are going on. 2 of them are a pain in the behind because of the scaling garbage. But actually, I do have part of what I need there. I think, can someone take 0.075 and type that in the calculator and get a fraction? Do math frac? Look at everyone, just look at me. No, I can't. Anyone have their calculator? Look at that. Everyone just look around. Look at them. Aren't you on like 3 lists? Or no, who was that? Was it him? Who was the one that was on? Is there someone that sits there or no? Maybe I'm thinking of last hour. Oh, it's last hour. Was it 3/40? Ooh, okay, that's what I got last hour. All right. Okay, so that's why I asked, hey, what's the y-intercept of this line? What's the y-intercept of this line? What's the y-intercept of this line? What's that number right there for y? 0. So this first piece is 3/40 or 0.075x, and that's it. Because the y-intercept is 0 plus 0. And then where is this defined? We're going to count 0 as a starting point, so it isn't equal to all the way up to 20 minutes. Now you have a choice here. You could make this equal to, but what I'm going to say in my head is this. At the 20th point, you're stopping and you're at the bank. So we're going to say step off. This is going to have not an equal to, but then we'll start with an equal to sign on the next one. It really doesn't matter because this is continuous, so they fill in each other nicely, so it's all good. Next one's going to be easy. What kind of line is this? Blue, straight, but it's also what? Horizontal. What's the equation of a horizontal line? Y equals a number, and that number is 1.5. Notice I don't put y equals again. I don't put f of x equals. F of x equals. F of x equals. All right, so it's already taken care of. The two worst ones are the next green and the next yellow. Those are going to be a pain. And it's no x on there, comma. So from 20, now, here's what I mean about this. I could choose to put this as equal or this. All right, it really is up to you when you're coming up with the equations of a piecewise function that's connected. These are connected, these are continuous. So this could float between these two. I want you to understand that I'm just making a choice. And that's what x is when I plug it in, and then that goes all the way up to 30, right? And then the same idea. We're going to say at 30 minutes, we're moving on to the next function. So let's put 30 in the next part. Okay, now we got a problem. I think the best thing to do is this. This is 30, and then I embarrassed myself last hour. I did 1.5 comma 30 because I looked at the y's first. So that's 30 comma 1.5. Then honestly, I think what's smart is to do this. This is 40 comma 2.5. And then you got to go to grade school. You got to find an equation of a line. So over here, here's the slope of this blue line. I'll do the work down here. It's 2.5 minus 1.5 over 40 minus 30. And it should be a positive slope. So this is 1, right? Over 10. So 1/10, right? And then what I don't have is the y-intercept. So I got to find the equation of the line. Pick any of the 2 points. I guess it really doesn't matter. I'll just choose the top one. Y minus y1, which is 2.5, equals m. I like this format. X minus x1. This is the hardest thing we have to do today. Watch the last example. It's like a piecewise of only 2 pieces. So this is like tough. All right. If you can handle this, we're good for the day. Y minus 2.5, and then 1/10 x minus 4. 1/10 of 40 is 4, and then add 2.5. So add 2.5, and I'll write the final answer up there, which is negative 1.5. So this is 1/10 x minus 1.5. Now, where does that happen? That happens from, I didn't do this wrong, right? 30, okay, so 30 to 40, right? So let's do that same philosophy. 30, you start leaving, and then at the 40 point, you make it to the next destination. Again, if you made these equal, that's fine, then these would be not equal. It's just a connection. To be more specific when we get going here. All right, next one's easy. This is 2.5, another horizontal line, and that's from 40 to 55, right? Let's say it starts at 40, and then at 55, you move on to the last one. Then honestly, Do I have to show you how to find an equation of a line anymore? Okay, I hope not. So this is 55, comma 2.5, and then make your life easy. The other coordinate is 75, comma 0. And then you do the same thing. Find the slope and then find the equation of a line. Okay, and then you put that right here. And then that last one is 55 less than or equal to x all the way up to 75, and it closes. We're counting 75 because 75, comma 0 exists. The 75 minute, you make it back. Okay, I'm just being lazy. You know how to find an equation of a line. Okay, whew, that's a mouthful, right? All right, so that was rough. Okay, this one's kind of weird, but you know, in reading this, what are they asking? Okay, we have another piecewise function there. You really should have this bracket here. So put this, or brace. Should always be a brace there, not just floating there. Okay, determine the values for x, which make these outputs happen. So these are y's. I need the x's that make this happen. Those are y and y. So 1. Could I ever get 1 out of this function underneath these parameters? Yes or no? Am I allowed to plug in 0 for this function? Yes or no? You're not allowed to. You're going to find out, though, you actually do when you make the picture, but it's going to be an open dot. This is not allowing me to plug in 0, so will I ever get 1 here? No. Will I ever get 1 out of this? This is literally just a dot. All right, this is at 2, comma 0, and that's just a dot. And then this is not going to be continuous if I graph this. We'll see the next one. Am I allowed to plug in 1 into the third part? Yes. What's 1 squared? I'm sorry. No, what do I have to plug in to get 1 as an output? The answer is still 1. Sorry about that. And then 4. Could I ever get 4 out of this? Could I ever get 4 out of this? No. You're going to be only plugging in negatives. This could never be 4. That will never be 4. How do I get 4 out of that? What would I have to plug in for x? 2. So those are the answers for those that kind of like a little tougher reverse analysis there. Okay, now we're actually going to graph these. Oh, all right, now we'll give the domain and range and behavior and all that other great stuff, analyzing stuff. Okay, now this is actually I could look at it and kind of tell this is going to be discontinuous. These are not going to be connected, so this is very specific what we have to do. And what I like doing is doing like individual charts for each piece following these parameters. So am I allowed to plug in -5 in the first piece? Yes or no, class? 3, 2, 1, go. No. And you should be answering that. So we're going to do this the wrong way. We're going to not do that. We're going to plug in -6. What did he just say? Anyway, I'm going to plug in -6. -6 times -2 is 12. 12 minus 8 is 4. And I'm going to happily graph that. 3, 4, 5, 6, 1, 2, 3, 4. And I'm allowed to plug in that point. And then maybe I'll plug in -7 for giggles. 14 minus 8 is 6 because of negative. And then 7, 1, 2. And then I'm going to do, I can keep plugging these in forever and ever and ever. So that means this graph goes forever and ever this way. Here's where you're wrong. What are you not supposed to plug in? Negative what? 5. But why do I plug that in? -10 minus 2, that's 2, is because from -6 to -5, what about this graph right there? I'm allowed to plug in -5.1, aren't I? Yes? -5.2, -5.3. So you have to plug in -5, but then put that as an open dot, meaning that's the end. I can plug in everything up to that point, so now I get that. I swear to dog, anyone that doesn't have that little part, I'm coming with the red pen of vengeance and getting you. All right, this is one of the biggest and most important things with a piecewise function, getting that little piece there. Rawr. Okay, then I'll talk about where people screw up on this stuff. I'm going to use colors on this. What kind of line is this? Horizontal. Okay, so y equals 6 from -5, 1, 2, 3, 4, 5, 6, including that point, all the way up to 1, not including that point. And there's that horizontal line, and that's why I knew this was not continuous. Now is the time to talk about the goofballs on piecewise functions. What I get with people that don't know what's going on with piecewise functions, they graph this whole line, they graph this whole line, and then they graph this whole line and this, and all these graphs are crashing through each other. That is not the point of a piecewise function. You need to read the domain. I'm hitting the back button. I don't know if it's working. So do not do that. Okay, there we go. These pieces must be like this. So covering some mistakes that people make. Well, here we go again. At x equals 1, I get -1. That's just a dot. That's why I was telling you about that in the previous one, which we didn't really, have a sense of that yet. So I can only graph that in one position for the domain. And then last but not least, hey, what color should I do? I did purple. I guess black. This is x times x minus 4 when you factor this. So the x-intercepts would be 0 and 4, but I'm not allowed to graph that. I'm only allowed to graph greater than 1. Do I plug in 1 though? Yes or no? What do I put after I plug in 1? Open or closed? Okay, open. 1 squared and a -3. So 1 comma 1, 2, 3, open dot. Another thing is, what kind of picture do I have? I should plug in some more points. But between 0 and 4, 2 would be the vertex. The x-intercepts are 0 and 4. So 2 would be the vertex. So I'll plug in 2. 2 squared is 4. 2 times 4 is 8. 4 minus 8 is 1, 2, 3, 4. I got a little scared because I knew this parabola should be facing up. When I plugged that in last hour, I wasn't thinking. Like, oh yeah, that's the vertex. That's why it dips down. And then when I plug in this value, 1, 2, 3, I get that value again. I plug in 4, I get 0. All right, so here's the parabola situation. Okay, definitely not connected. This is discontinuous, and they do ask that. Okay, domain. When you look at these domains go forever backwards to -5, include -5 to 1, include 1, and then everything greater than 1. What's the domain? All, anyone? All real numbers. So domain is all real numbers. Doesn't always have to be the case. Our domain wasn't all real numbers in the previous, from 0 to 75 minutes, going home and coming back, or going out and then coming back. Had a defined set of parameters. And then the range. I know there's a bunch of gaps here, but this graph covers all these range values, so it really covers everything else. Couldn't care less about this because this covers all those y values all the way to there. So actually the range is -4 to infinity. So that is a little limited. Okay, don't ever do this. But as I go left and right, both limits are the same. The limit of f of x, here we go, we're going to be lazy. As x approaches both plus and minus infinity, both of them go to infinity. It's the first time I've ever did that, but I do shorthand because I don't want to blabber like this too long during the notes. Name the x values where g of x is not, this is called g of x, not continuous. I think you see that. That's -5 and 1. At -5 and 1, we got those jump off points. We only have one absolute minimum of, let's say this the right way, -4 at x equals 1, just to remind you of all that. And then I'm not going to write the increasing, decreasing constant. We're just going to verbalize it. What's my hand doing from here to here? What's it doing? Decreasing from -infinity to the x value, -5. Increasing and decreasing, you always use parentheses. All right, that's just it. All right, what are we doing from here to here? Constant. What are we doing from here to here? Shucks. Decreasing from 1 to 2. And then increasing from 2 to infinity. All right, so just know how to name that. All right, and then this isn't so bad. I can actually answer these questions just by looking at the picture. Here's -8 and -6. What's the average rate of change? It's just the slope of this line, which is what? Look at the equation up there. What's the slope of that line? You're killing me, guys. Negative what? Negative 2, right? So that's negative 2. Maybe we'll do this. And then from negative 3 to 1. Come on. What is it from negative 3 to 1? What's the average rate of change from these 2 points? We should know that the slope of a horizontal line is 0. Not undefined, that's a vertical line. All right, and this one is a little bit different. 3 to 10. Okay, so that is this piece. 3, first of all, 1, 2, 3. This is 3 comma negative 3, right? Just wanted to make sure. And then I actually need 10 comma. That's not even on my grid, so I have to get that. 10 comma. Well, 10 squared is a hundo. 10 times 4 is 40. That's 60, right? So what is the average rate of change there? 60 minus 3, which is 63, over 10 minus 3, which is 7, right? Okay, that's the average rate of change between those 2 points. It's just the slope between those 2 points. And that's all you got to do on that. All right? Oh. So I think I did do this one real quick. I think I slapped it down here. Maybe I did run out of time. I don't know what happened last hour. What time did we get out of here? 55. Do you want to do this one? All right. Should I? Let's just go ahead. Okay. By the way, this is a picture of a what? Anyone? What's this a picture of? Oh my gosh. Okay. Let's just go ahead and do it. All right. It's supposed to be V. All right. So I did do this one last hour. Okay. Now, I am allowed, or am I supposed to plug in negative 3? Yes or no? Should I plug in negative 3? Yes. What kind of dot do I put there? And by the way, where is the vertex? This is what I mean about knowing your stuff. Where's the vertex located? Negative 4, comma 0. So negative 4 is comma 0 is the vertex. I don't know why we didn't give you axes. I think just going right in the middle of both x and y is fine, and you'll be all right. Okay, so negative 4, 1, 2, 3, negative 4 comma 0. Negative 3 plus 1 or 4 is 1. 1 squared is 1, but open dot. And then negative 5 is negative 1 squared, which is also 1. So this is what I got. I got my parabola that's going like that. But it's got to stop right there, and that's got to be an open dot. Has to be. Next one, I guess we'll color code that in green. Now I want to plug in negative 3, but where's the vertex of this? Where's the vertex of this V? I'd like to know that, and is it in my parameters of plugging this in? What do I plug in for x to get the vertex? Negative 1. What do I get as an output value? 2. So, and I can at Lockport, I can plug in negative 1 because it is in these parameters for the domain. But I also want to plug in negative 3 and 1. So negative 3 plus 1 is negative 2. Absolute value 2. 2 plus 2 is 4. 1, 2, 3. 1, 2, 3, 4. And it is a closed dot. And then 1 gets me that same thing. 1, 2, yep. 1, 2. But it's an open dot. Okay, what I was doing is these are symmetric points for the V scenario. But I'm not allowed to plug in 1. You don't stop at 0. You got to get that little part there as well. All right, and then square root. I hope I did this right last hour. I am allowed to plug in 1. What's the square root of 1, everyone? So 1 comma 1 is a filled in dot. This is funny. What's the square root of 4? Some people told me 16 last hour. What? Okay, and then what's the square root of 9, which is off the board? 1, 2, 3, 4, 5, 6, 7, 8. It's not. What's the square root of 9? 1, 2, 3. What you get here is like a half of a parabola going sideways. This is actually curved. We actually graphed those last year, September, October. We did a lot of graphing and did all that. Oh, continuous? No way. Domain and range. Domain, again, is all real numbers because we go less than negative 3, include negative 3 all the way through greater than 1. But the range is 0 to infinity. Not continuous. You can see those. We have a minimum And then decreasing, increasing. I hope you're okay. What is this doing? What's the blue doing? Increasing. This is increasing. This is decreasing. Increasing, decreasing. We would have to separate all of these because they are separated in jump off points. So you'd have to name 1, 2, 3, 4, 5 different increasing, decreasing intervals. All right. And then average rate of change. Do you get that? You guys okay with that? All right. From -5 to -4. So 1, 2, 3, 4, 5 to 4. It's just the slope of that line, which is down 1 over 1. That's -1. -3, 1, 2, 3 to -1. That's just the slope of this V here, which I think was -1, right? As well, correct? Yeah. Then 4 to 9, you'd have to input, say it. Well, actually, it's a lie. I do have those 2 points. Rise 1, run 2, 3, 4, run 5. Right? So easy. Okay, and then who cares? Concave up, down. We got it. What's this concavity? Concave up. I don't know if you really should call linear stuff concave up because it doesn't really pertain to what's happening in this scenario. So we got to be careful on that one. All right. Okay, domain and range. I guess that's pretty good, and we have time to do this. The domain. Well, this domain is actually limited because there's no arrows. So the domain, and those are all closed-in dots, that is from -5 to 6. That's domain because it does say range, and the range of f. The range looks like it only covers from -3 to 1. So the ability to read that graph and then see that those are the y's that are covered. Y's, -3 to 1, filled in dot, so I can include them. Those are brackets. Identify 2 intervals that would have a positive rate of change. Okay, what a positive rate of change is talking about if the graph is increasing. So I did want to do that. I should have maybe done that thing over on the graph here. Let's look at something and add a little piece here. So here's h of x. This is something I want to synthesize here. And go ahead and draw like this curve. All right. And then let's say we had an input here and we've got it like, okay. What is h? Is h positive or negative? Hold on, don't answer that. Oh, sorry. I didn't get my E in there. I often do that. I skip a letter. And then what is h doing? Is h increasing or decreasing? And then what is the rate of change? I did it again. I keep losing my A's. Rate of change of h. Is it increasing or decreasing? What? Okay. So input, say it. So what is h? Is that output or input? What's h mean then? So h of x. So what's h? Input or output? Output. We should know that from notation. That's number 1. What is h? Is it positive or negative? Notice my y and x axis. What is h? Positive or negative? Negative. This is just what kind of y value is it? All right? That's what that means. But this is different. What's h on what interval? On an increasing or decreasing interval? Which one is it? Decreasing. Okay, it is on a decreasing, so that means the slope of this tangent line would be negative. And I do want you to understand that too, and we got to start thinking about that because I think I have discussed that with rates of change. What we ultimately want to do is not an average rate of change of 2 points far apart. We want to drag them together to make it a tangent line slope, and that's called instantaneous rate of change. And this slope is definitely a negative number. So when you have a negative slope of a tangent line at a point, it just means you're on a decreasing part of the curve. You got it? Okay, what's the rate of change doing though? What this means is as I'm moving through this interval from right to left, what are the rates of the slopes of the tangent lines doing? Well, let's not overcomplicate it. Is it concave up or concave down? That's concave up. So what's going on with the rates of change? Are they increasing or decreasing? They're increasing. So I wanted you to know those three different things. I think we did a really good job with regular AB in making those disseminations, those little points. But really, why is that occurring? As I keep moving along this little interval, you have to understand that that line and that line, what's the difference between the two? Now let's make up some numbers. What time do we got up there? 47. We're good. What do we leave? When do we get done? Oh, we went right to the bell. People were packing up, and everything. All right. Do you know that this slope might be something like -6? I'm making up a number. So drop 6, run 1. Does that make sense? So wouldn't it make sense that this slope is like not -6? It's like -2, right? Wouldn't that make sense because it's less of a drop and run? What number is bigger, -6 or -2? Who's bigger? -2. So what's happening with these slopes of tangent lines as you move left to right? They're going up. That's how you analyze and why this is happening when you're looking at a concave up graph. What is the rate of change doing? So the slopes of the tangent lines keep going up as you move left to right over this little interval. So I do want you to know that as pertaining to like those questions right there. But really, as we get done with time, I just want to actually define this. Okay, so what did they call this? So they call this f. So this is f of x again. This is not even close to as hard as what I had you do with the leaving home and coming back to the bank and the store. This first piece, by the way, has a y-intercept of 0. I'm better here that I do have a nice little set of points with a good scale. So rise 1, run 2. 1/2 x is that first part, and it's defined from -6 to 2. Now again, -6 including to 2. Now again, you have a choice. This is a connected continuous graph. If you made this an equal to part, then the next part starts with a not equal to part. But I'm just going to say, I'm going to go in the idea that I'm stepping off and going to the next one, so I'll include it here. And then this is what you got to know about this. This is vertex form of a parabola, and I'll put this in purple. So this vertex is 4, -3. So is that x plus 4 or x minus 4? Which one is it? It's minus. Why? This got to be what when I plug in 4? What does that got to be on the inside? 0. And then down 3. And then one more thing. Do you remember this last year? If you can see that this rises 1 and runs 1 for the first order differences, I know why I have time. I didn't go to the previous notes, did I? And do the order differences thing. What time do we get out of here? Son of a nutcracker. I want to hit the wall right now. I thought I had such good timing and I forgot to do something here. But anyway, that proves that that's 1 in front. Okay. So that's kind of tough coming up with an equation there. But it is from 2 less than or equal to x all the way up to 6, including 6. I'm a bum and a charlatan and a fraud. I forgot to do this. I was in here too, wasn't I? And then I forgot to go back up here. Okay, sorry. Can you get your notes out real quick? I'm going to do this real fast. And then I'm going to verbalize it, and then we'll be done in the last 5 minutes. So we are going to go to the end. And then what you can do is turn in 2 assignments tomorrow. And then we'll be good. My bad, dogs, but you're an honor, so you should be able to handle this. Okay, now, the part of the notes that I didn't cover. So I did go to this, and I talked about graphing again, and then I forgot to go back up to here, order differences. Okay, look at these equations, x squared and -2x squared. Here's what they did. They put the chart of values down here. Input, say it. So here's x squared, here's -2x squared. By the way, we got a problem. These are all negative. If you go ahead and input those, you'll see that those are all negative. So this is what eventually it's going to happen to you. You're going to have a chart of values, and you're going to figure out what function matches this. This is how you do polynomials. X to the first, x to the second, x to the third. You do order differences. What's the difference from 9 to 4? What happened? Down 5. What's the difference 4 to 1? Down 3. What's the difference 1 to 0? -1. 0 to 1. 1. 1 to 4. 3. 4 to 9. You see a pattern, but what you see is these are not all equal. So this is called first order differences. First order differences. I gotta hide this. I don't know why that's there. And they're not equal. But here's what this is. Look at this. This represents this part of this graph, which I did highlight in yellow. What's that graph doing in the yellow? It's decreasing. So when your order differences are negative, that means the graph is decreasing. First order differences are negative. And when they are positive, that means the graph is increasing at that stage. Okay? But what I don't have is this is not an x to the first function. This is not linear. If the first order differences were equal, that would be the slope, the constant rate of change. Does that make sense? Every y value. By the way, be careful on this. Do double check that the x's go up by equal intervals before you check the y's, and they do, luckily. But then look at the second order differences. -5 to -3 is what? Isn't that up to, right? And then up to, then up to, then up to, then up to, right? So the second order differences equal, second order differences, when those are equal, I feel like I like this. When they are equal, that means a quadratic mirrors the data, which we know. We saw that. We knew it was a quadratic. We knew it was an x squared. In the future, you're going to get data values, and you're going to have to tell me, is this linear, quadratic? And then we're going to expand. Exponential, logarithmic. You know, there's other different things you got to test and find out. But notice the second order differences. They're positive. What's the concavity of this graph? Up. Positive second order differences mean concave up. Then when we get into cubics, the second order differences are not equal because it's a cubic function, but where there's positive differences, that's a concave up portion. Now, when you actually do this, you can go ahead and put your stuff away. I'll go ahead and finish this. -18 to -8, that's up 10, up 6, up 2. -8 to, oh, then these are negative. So this is down 2, down 6, down 10. But then when you find these order differences, these are -4 for the second order differences. So again, equal, so it's quadratic, but negative second order differences, that means concave down. And that's exactly what happens with our second quadratic. So sorry for going back to Friday's notes and finishing off what was quite long. I really did want to do those AP videos Friday, though, so I was happy that I did that. Okay. Bye, everybody.
Hi, Mr. Samuels.